Data and information are all around us in our daily lives, and it's becoming increasingly important to understand how this data is being collected and used. Differential privacy is a mathematical framework that safeguards individuals' privacy during data analysis. It is essential for sensitive data like medical records and financial information, where privacy breaches could have grave consequences. Differential privacy also maintains the usefulness of data for its intended purpose, such as research or analysis, achieving the goal of protecting privacy without compromising data utility too much. For instance, many of us have experienced the feeling of finishing our favorite series on Netflix and wondering what to watch next. Fortunately, Netflix uses their recommendation system to suggest new content based on our viewing history and preferences. But have you ever wondered how the mechanisms behind Netflix collect and utilize your personal data to make those recommendations? It's a complex process that involves analyzing large amounts of data about your viewing history, as well as data from other users who have similar viewing habits. And with so much personal information at stake, it's crucial to ensure that the data is being handled in a way that ensures privacy and protects sensitive information. Unfortunately, Netflix failed to do this a decade ago. In October 2006, they launched the famous Netflix Prize Challenge, offering a $1 million prize to anyone who could improve the accuracy of its movie recommendation algorithm by 10%. Therefore, Netflix released a dataset of over 100 million movie ratings made by its users, anonymized by replacing user IDs with random numbers. However, researchers were able to re-identify some of the users in the dataset by combining the Netflix data with publicly available data from the Internet Movie Database and other sources. For example, one user was re-identified by matching his Netflix ratings with his public IMDb ratings and comments. This incident showed that even innocent data such as movie ratings can be used to re-identify individuals when combined with other publicly available data. And we all know we share a lot of ourselves online. It highlights the need for more advanced privacy techniques, such as differential privacy. Let's introduce this concept using an example. Let's say we held a fictional poll about the student's favorite big data science professor. Would you like to participate in this poll if it is not anonymous? Students must choose between Blue Brainiac, Orange Oracle, and Green Guru. Luckily for our hypothetical participants, we are only interested in some specific statistics such as the overall favorite professor and the favorite professor of students who passed the class. The Orange Oracle is the overall favorite. However, when we look at the favorite professor of the students who passed the class, we see that there is a tie between all three professors. Since there is only one student who failed the class, it's easy to see that when combining these results, we can identify the vote of this student. So how can we prevent this from happening while keeping the accuracy of our statistics as high as possible? Since this is no new problem, we will apply some existing techniques on our datasets. These techniques are also called disclosure avoidance methods. We can swap some records in the field of study column, reduce the precision of the marks column. Additionally, we can introduce randomized response where we first flip a coin. If it's heads, we tell the truth. Otherwise, we randomize the response, giving the person plausible deniability. This way you can never be sure if his answer was truly his, or just a random pick. In our example, we flip a coin for each vote and randomize the response which the coin landed on tails, thereby changing 2 out of the 7 votes. Last but not least, we can add some random noise to the age column. These are all very nice and effective techniques, but when we are looking at our new dataset, it is hard to see exactly how effective our transformations were. Have we removed too much data, and is this dataset unusable for our specific use case? Or even worse, did we overlook something, leaving the dataset vulnerable to leakage of private information? Enter epsilon differential privacy, a mathematical formula to measure the maximal possible leakage of private information when using disclosure avoidance methods. The formula is based on one key concept: the removal or addition of one entry in a dataset can only have a limited effect on the inferred statistics. Otherwise, the difference between these two statistics might give away information about this one new record. When you look at the formula, however, you might not be convinced yet. Let's break it down together step by step. We will start by defining D1 and D2. These are two identical datasets apart from one dataset having an extra entry. The formula also holds when you swap D1 and D2. A is a random algorithm over a dataset. As an example, our random algorithm looks like this. Given a dataset, we count the entries and add some noise. We perform this randomized algorithm A on our datasets D1 and D2. We can interpret the output of A on dataset D1 and D2 as two random variables centered around X and Y. For perfect privacy, you would want these distributions to be identical because then we would not spill any information about the extra record. To measure the difference of these distributions, the formula of differential privacy is used. The formula divides the area under the curve for all possible subsets of these distributions. The maximum value of these divisions will then be equal to the exponential of epsilon. The maximum difference of the outputs of the count queries is 1, as the dataset only differs in one entry. This is called the sensitivity of the query. If we now add noise of the Laplace distribution with parameter b, turns out that epsilon is equal to 1 over b. But how can we interpret epsilon? An epsilon of 0 would mean perfect privacy, however the data will only be noise. On the other hand, we can only achieve perfect accuracy using an epsilon of infinity. This would imply that there is no privacy. Epsilon differential privacy also has some nice properties. The epsilon value of a group of C people is C times epsilon. Moreover, doing K queries would mean that you would have to take the sum of the epsilon of each of these queries. Lastly, if your data is obtained in a differentially private way, any post-processing done on this data is still differentially private, as long as you never return to the original data. Coming back to our example, the differential privacy would be the sum of the two queries we made. We now have a metric to measure a potential privacy leakage. However, how can this metric be used in practice? It turns out that big companies have recently published how they use differential privacy to be more transparent over the privacy they provide. They do this using a privacy budget. This is the maximal composed epsilon over all their collected data. For example, Apple granted their emoji dataset an epsilon of 4. Other datasets also received some budgets based on the utility and privacy needs of the data. The total of these is an epsilon of 30. This is a policy of Apple. If this is too much is up for further debate.